We're excited to be here today to present our work on Treeline, which is a new update-in-place key-value store for modern storage. So this is a joint work with many people. So I'm Jeffrey.
I'm Marcos.
And it's also joint work with Andreas, Paul Larson, Umar, and Tim at MIT. So let's get started.
So we'll begin with some motivation about what led us to pursue this project. The overall idea is that key-value stores abound in today's context, but not all keys are created equal. Main applications that see key-value stores online are things like storing configurations, storing user preferences, or storing profile metadata for applications like social media. However, on all these domains, you see keys of varying hotness, where the hotness itself is independent of the key value. So it's not like a timestamp where the most recent keys are the hot ones. Moreover, frequently updated and frequently read keys are not necessarily the same. You can imagine that some attributes are used very often, so you need to read them, but they're not updated as frequently. Finally, updates tend to dominate inserts. It's rare that a new field will come into play, but updating the existing fields might be very common. The big question then is how to handle such a workload efficiently. In general, many of these applications tend to use LSMs or log-structured merge trees to support such workloads. The basic principles are as follows. You first use an in-memory structure called a memtable to buffer writes in memory. And once it becomes full, once it hits a fixed size threshold that is, you flush it to disk into a single file. While you're flushing, you need to still be able to support user requests. So you lock the current memtable as immutable as it's being flushed and accept user requests in a second memtable to continue serving users. By following this process and alternating between the two memtables, you end up with a bunch of files on disk from all these different flushes. Of course, at read time, this can become challenging since you have to look into all these files for a key. So over time, what you do is you periodically compact these files into larger runs in a logarithmic manner. So all of these first files are labeled as level 0, and you have further levels like level 1 and level 2. At read time, if you're lucky enough and the key you want to read was written recently, you can access it from the memtable. Otherwise, you need to hit the levels on disk, blocks of which are cached in the block cache in memory. Lower numbered levels, of course, have fresher versions due to this compaction scheme. The benefits of this approach is that writes are efficient because new values are dumped into a memtable and then flushed all at once. But of course, reads are slower and memory use is high exactly because the key can be present in multiple locations. You can imagine the other extreme in terms of design, which would be an update-in-place structure like a classic B tree. There you have efficient reads because there is only one physical location where each key can be, the page that corresponds to its key range. However, writes might need random I/O because for an arbitrary write, you need to find that one right place to put the key in. And this is much worse than sequential writes in HDD. LSMs are more widely used for these applications exactly because of this trade-off, because avoiding random I/O at all costs was very important. However, the storage landscape has since evolved. With NVMe SSDs, random write performance in terms of throughput is almost equal to the sequential one, especially under high parallelism. So here on the left, you can see a plot where the x-axis is the number of threads, so a degree of parallelism, and the y-axis shows the throughput for random writes of different sizes. As you can see, especially for 16 threads, random writes perform exactly as well as sequential ones, and in general, you can see that larger requests tend to perform better. However, sequential reads are still much better than random ones. This is because of features that the disks themselves provide, like speculative prefetching, which means that even though the write behavior doesn't differ that much, the read behavior is still very different. Even so, you can see between these three lines that random reads of large sizes perform better, which will become relevant later. So given this new storage landscape, can we bridge these two extremes and create a design that is update in place, but is still competitive against LSMs on writes while still excelling at reads? And we believe the answer is yes, and our system Treeline addresses this one. So let's start with a classic B tree-like design here on the right, and let's see how we can make it efficient for the types of workloads we mentioned earlier. In such a design, point reads and updates will hit the cache first, so the buffer pool, or the block cache, as LSMs and classic B trees call it. However, as we saw in applications like the ones we want to support, hot records might be randomly distributed across pages. And then you have the problem of caching entire pages just because a single hot record is somewhere inside them. Instead, our first key idea is to replace this page cache with a record cache instead. This leads to lower memory amplification because only the hot records themselves are cached. at the cost, of course, of higher I/O amplification, because when you're flushing the disk, you still need to access pages. Still, we'll see in our evaluation that the balance of these two competing demands ends up in our favor. Okay, so point requests can be served efficiently through the record cache, but what about scans? So as we saw earlier, random reads tend to be faster than smaller reads. When we're scanning a lot of data, we'd like to make the reads as big as possible. To achieve this, our second key idea is called page grouping. The idea is to collocate pages into larger segments, and then for scans, read the entire segment in at once. This lets you achieve a higher throughput on these SSDs. Still, when you're doing point requests, you can still access the individual pages by using linear models to navigate within the segment. So this way you get the best of both worlds in terms of page size. Finally, for inserts, this updated in place design, like B-trees, only provides a single good location, a single designated location rather, for each key. But it might be the case that the page that this key needs to go on is already full. To avoid this scenario in every case, you need to leave some amount of empty space on each page. However, how much space to leave is an optimization target. On the one hand, leaving too much empty space would lead to bad I/O amplification, because whenever you read the page, you're mostly reading empty space at that point. However, leaving too little empty space would lead you to need to reorganize your data all the time. To bridge these two extremes, our third key idea is insert forecasting. There we use a recent sample of inserts to predict the location of future inserts. And then whenever we need to reorganize a full page, we leave an appropriate amount of empty space to anticipate the load of inserts coming in the near future. We also make limited use of overflow pages to further limit the reorganization we need to apply. Overall, that's our design, and now Jeff can walk you through the evaluation.
Thanks, Marcos. So yeah, let's take a look at how well all of these ideas work in concert. So here's our experimental setup. We're running on a 20-core Intel Xeon Gold machine with 128 gigabytes of memory. Importantly, we're using a Intel DC P4510 NVMe SSD, and that's sized at 1 terabyte. We're running the YCSB benchmark suite, and this is a standard benchmark suite used for evaluating key value stores. We use both the synthetic data set that comes with YCSB as well as real-world data sets, in particular an Amazon review data set that has 33 million keys, and we set it up so that 33% of the data set is able to fit in memory. We run both on uniformly and Zipf distributed requests. We compare against two key baselines, the first being RocksDB, which is an LSM-based design, and it's a production-grade key value store. And the second is LeanStore, which it's a state-of-the-art update-in-place-based key value store. We are looking at two key metrics, the most important of which is request throughput, but we also examine the amount of physical I/O performed to help us understand the differences in performance. So let's take a look. Overall, Treeline shines across the board, and in summary, it's doing about 2x better than RocksDB and LeanStore on average on point workloads, and about 2.5 to 2.8x on average on the scan workloads. We have a lot of experiments, so we encourage you to take a look at them for more details in the paper. But we did want to highlight a few of them and go through some intuition as to why Treeline achieves its performance benefits over its baselines. So let's take a look. First, we'll take a look at against RocksDB and on point workloads. And the key reason why Treeline does better on this workload is that Treeline is able to read much less physical data from disk. It doesn't need to access multiple levels that RocksDB might need to do in its LSM when performing reads. And it doesn't need to run compactions in the background, whereas RocksDB does. In comparison to LeanStore, the reason why Treeline does better is mainly because of better cache utilization. So like Marcos described earlier, we use a record cache to only cache the hot records in memory. And this leads to much better memory utilization, especially when the keys are small relative to the page size. In comparison to RocksDB on scan workloads, Treeline does better because it is again able to read much less physical data from disk. When RocksDB does a scan, it needs to merge records from all the levels in its LSM tree, whereas for Treeline, there's just a canonical range of data that it needs to look at. Against LeanStore, what's very interesting is that we have very similar designs structurally, but the reason why Treeline is able to do much better is because of this key idea of page grouping. Since we co-locate logically consecutive pages together physically on disk, we're able to make much larger reads from disk, and this allows us to achieve a much higher physical throughput, which leads to the better performance relative to LeanStore, which needs to read small, scattered pages on disk. So let's take a look at how all of Treeline's key ideas work together. So we ran a factor analysis where we successfully enabled each of the optimizations one by one, and want to take a look at how each of them affect the overall performance. So on the plot here on the x-axis, we have all of the YCSB workloads. So in particular here, the E workload is the scan heavy workload. And then the y-axis is the throughput in thousands of requests per second, so higher is better. So we start by plotting out the performance when all of the optimizations are disabled. So that's the light green that you see. When we enable record caching, you see that all of the point workloads get a big boost in performance, and that's because Treeline is now able to have much better memory utilization. So it utilizes the memory in its cache better, and this leads to far better performance on the point workloads. But what's also very interesting is once you enable page grouping, you see that the scan heavy workload gets a big boost, so its performance doubles in this case. And that's because it's achieving far higher physical read throughput, which is due to the performance property of the SSDs. And very importantly here, you notice that none of the point workloads are negatively affected by page grouping. So this means that you're still able to read small individual pages when you need to read just single point records. On the forecasting side, we want to see how well forecasting can do on reducing the amount of reorganizations that Treeline needs to do, which will lead to a boost in performance. So on the figure on the right here, we ran a 50% insert, 50% read workload on the NYC taxi dataset. The light green is running Treeline with no forecasting at all. And then the brown represents running Treeline where it has perfect knowledge of where all the inserts are going to be performed. So it doesn't need to do any kind of reorganization. And you can see with forecasting, which is this green bar, on 64-byte records, which are pretty small relative to the page size in Treeline, we're able to close more than half of the gap between no forecasting and having perfect forecasting. But on the 512-byte case, which are much larger records relative to the page size, there is still some more room for improvement. But overall, this shows that insert forecasting is able to boost Treeline's performance just by leaving the appropriate amount of space based on where it expects inserts to come. And the reason why the 512-byte case does not do as well is because there's less granularity available on the page. There are fewer records that can actually fit on one of Treeline's pages in comparison to the 64-byte case. So there's many more details in the paper that we didn't have a chance to get to in this talk. This includes implementation details about concurrency control, durability, recovery, other experiments that we didn't get a chance to cover, as well as some more discussion about interesting extensions to Treeline. So we wanted to conclude with some key takeaways. With NVMe SSDs, parallel random writes are now approaching sequential random writes in performance, and especially in throughput. And this is an opportunity to revisit key value store design. So Treeline takes advantage of this by proposing 3 key ideas to adapt, update, and place-based key value store designs to this new performance paradigm. And that is having record caching to get more efficient use of memory, page grouping so that scans can leverage the better physical read throughput, and having insert forecasting to proactively leave space for inserts. So overall, we evaluated in YCSB and we're doing about 2.2x better on RocksDB and LeanStore on average, 2.5 to 2.8x better than RocksDB and LeanStore on scan workloads. So thanks for listening to our talk. Please check out our work and we're happy to take questions. Thanks.